Okay, here we are, week 3, Calc 1, day 12, chapter 4, section 2. Now we're going to get into the definite integral. So the definite integral means it's going to have a beginning and the end. It has a start point and a stop point. So we're going to use what we looked at in the last section. We have the limit as n approaches infinity. I will go from 1 to n, and again, f of x sub I asterisk. If you remember, the asterisk means that I'm not going to use my left point or my right point. I'm actually going to use the point that touches the graph, and then times my width. So this is what we looked at in section 4.1. And this, in fact, does define our definite integral with our upper and lower limits. We call this our lower limit. We call this our upper limit of f of x dx. Now, this integral sign here and the dx are assembled together. They're not separate. This just tells you with respect to what variable we're looking at. And then this is our function. Okay, so now we have this equaling the limit as n approaches infinity of 1 to n of what we just looked at, f of x sub I asterisk, and delta x is the width. So what we're saying is that when you find the limit of this, you will be finding the definite integral from a to b. Okay. Now, the precise meaning of a limit, and we looked at this in the last chapter, what we're saying is that when I take that limit of that function, okay, when I get this value of the limit of this function, then if I subtract that from my definite integral, it'll be less than that little epsilon. Remember, that little epsilon is that small area that I want to be in accuracy of. So I might say I need it to be within 0.01 because that's the accuracy that I need for what I'm doing, and that's what the little epsilon would be. Now here's just some definitions of this. Is in fact an integral sign. You have your upper limit and your lower limit. They remind you that the integral sign and the dx are together as a symbol, and they let you know that Leibniz, who is the mathematician who developed the integral sign, he chose this sign because it looks like an elongated S, and it actually means the sum of all those little triangles that we looked at before. So that is why the integral sign looks like an elongated S for sum. Okay? So this definition is called a Riemann sum after the German mathematician Bernhard Riemann. And as everything in, well, not everything, but most everything in mathematics, they get named after the mathematician that was responsible for publishing that work. Not necessarily the one who first discovered it, but the one who published it first. Okay. So let's go over here, and again we are just reviewing what we looked at in the last section. And here I have this curve, here I have my a to b, here I have my x sub I and my asterisk that comes up and actually touches my curve, and then I have my width, which is delta x. So if f is greater than 0, the Riemann sum is the sum of these areas of the rectangles. What does that mean? Well, notice that everything in this picture is above the x-axis, okay? But that's not always going to be the case. For instance, if you take a look over here at this graph, we have these areas that are above the x-axis, but we have this which is below the x-axis. So you have to make up for that because you're actually wanting to add the areas together. So you have to subtract the negative area to make it positive. That's what this means. the sum of the positive areas minus the sum of the negative areas will give you your net area. It's kind of like taking the absolute value of it so that you're just adding all the positive parts. Okay? So again, here we have positive, negative, positive. We're going to be adding these two and then subtracting this one because we need to make that positive as well for the net area. Okay, and again, we're reminding that the width is still the b minus a over n, how many little sections you're going to look at, and this is our beginning lower limit to our upper limit, and we're just going to be adding all those sums of the rectangles together so that we can get the closest sum possible. And we get the closest sum possible looking at as n approaches infinity. So I want to have 1,000,000 rectangles. That will certainly help making my sum accurate. But even better than 1,000,000 would be infinite. All right, now we're going to look at how do we evaluate. What do we use these for? Here we have the limit as n approaches infinity from 1 to n of this function. So we have x cubed plus x sine x. And then this is times our width, delta x. So here we have our length times our width. And we're going to look at it on the integral, look at it on the interval of 0 to pi. So we're looking at it from 0 to pi, which means we're looking at the limit as n approaches infinity of 1 to n of this value times x. All these little rectangles together as n approaches infinity. And that will give me this symbol, which is the integral from 0 to pi of x cubed plus x sine of x delta x. And again, I want to remind you, or dx. I want to remind you that dx and the integrand are a symbol together. Okay, apart they're nothing. Symbol together. Excuse me. Okay, so let's take a look at evaluating integrals. We have found through different formulas that there are ways that we can simplify by people already proving, just like in geometry, once you prove something, you can use it. So we found these values that we can use to prove. We found out that from I to n of the summation of just I will reduced to be n times n plus 1 over 2. This is the one that we looked at for the parabola already. It would be n times n plus 1 times 2n plus 1 all over 6. And here's my cubic function, n times n plus 1 all over 2 squared. So these help us to reduce and solve for our answer. Now, some simple rules for working with sigma notation. Some of the same things that we looked at with limit. If I have sigma of a constant, well then I'm just going to take the number of times that I'm going to take that constant and multiply it by that number. So let's say I'm going to do it 10 times. I'm going to take 10 times that constant. Here I am reminded that if I have some kind of expression and it's all multiplied by c, that I could actually factor out my c, do my sum first, and then multiply by my c. Number 10 says I could find the sum of the first one and the sum of the second one and then add them together, or add them together and then take the sum. And again, the difference, you can also do the same thing. Okay, let's take a look at example 2. And then I'm getting tired of just looking at the book, so let's write some of this out here. Maybe I'm hoping that that will be helpful. Okay, let's see. I'm going to turn this. Okay, so example 2 says we're going to evaluate the Riemann sum for f of x equals x cubed minus 6x. We're going to take points from the right and I'm going to say a equals 0, my starting point, b equals 3, and I'm going to use 6 rectangles. So when I look for my width, then my width will be 3 minus 0, that's my b minus my a, over how many rectangles I have, and I see that my width, or my delta x, will be 1/2. So 1/2 is what I'm going to use for each one of these rectangles. Now, keep in mind, I realize that I have 6 rectangles and they're all to the 1/2. And if I'm going to have some kind of curve, if I have some kind of curve like this, which is what this one looks like, okay, and I'm going to be estimating from 0 to 3, okay, and my width is 1/2, and I'm using my points to my right, not to my left, but to my right. So that means my first point's going to be at 1/2, my next point's going to be at 1, my next point's going to be at 1.5, my next point's going to be at 2, then it's going to be at 2.5, and then 3. And I know that's not to scale, so sorry about my bad drawing. Okay, so my x sub 1 point is 0.5. My x sub 2 point is 1. My x sub 3 point is 1.5. My x sub 4 point is 2. My x sub 5 point is 2.5, and my x sub 6 point is 3. Okay, so here I have my width, and I have my points on my right that I'm going to use. So how would I figure out what my sum is there? Well, I'm going to take my f of x, and I'm going to substitute in that 0.5 and multiply it by delta x, which is my width. And then I'm going to take my 1 value and multiply it by my width. And then I'm going to take my 1.5 value and multiply it by my width. And do the same with my 2. Multiply it by my width. And 2.5. Multiply it by the width. And finally, my 3, multiply it by my width. Now, of course, this is going to look a little bit messy. What I have to do is substitute this value into my function of f. So I'm going to take over here every one of these values and put it into my function so I can get my values that I'm substituting in. So when I take a look at that, I'm going to get negative 2.875. I'm going to get 5. That's a nice one. And actually negative 5. And I'm going to get negative 5.625. And then I'm going to get a positive 0.625 and positive 9. I skipped a number somewhere. What did I miss? Okay, this. Oh, I missed a minus 4, sorry. Okay, So this is putting these values into f of x. So if this is my x, I just put these values into my f of x up here because I'm going to need that for figuring out what my Riemann sum is. Now, I noticed that my delta x for all of these is 1/2. Remember, it's always the same. So that would mean I'm going to take 1/2 times these values, negative 2.875 minus 5 minus 5.625 minus 4 plus 0.625 plus 9. Okay? And then when I add all these together and take half of that, I find out that I will get a value of negative 3.9375. Now, notice that f is not a positive function, so the Riemann sum doesn't represent the area of triangles, but it does represent the sum of the areas of what they call the blue rectangles minus the sum of the areas of the gold rectangles. So here we have, if I take the blue minus this, you can see this is much bigger, so I'm going to end up getting a negative value here. Okay? All right, now part B says evaluate this as an integral. So I'm going to evaluate from 0 to 3, x cubed minus 6x, and this is where those of you that have had calc before are probably shaking your head and saying, why are we going through all this when I know how to solve this quickly? But as I mentioned before, it is important for us to know the background of what this actually stands for. Too many times we learn the formulas and have no clue what they represent or what the application is. So here I have my limit of f of x, delta x, and I'm going to substitute in for that my f of 3I over n times 3 over n. Okay, now why is it 3 over n? Because I'm looking as n approaches infinity, so what I'm saying is that my n is no longer 6 little rectangles. My n is, let's see if we have infinity rectangles, how close that we can get to that. All right, and then in order to do this, then I'm going to take my limit as n approaches infinity. Now my 3 over n is going to be my width value, so I can actually pull it out because it's a constant, and I'm going to look at my sum from 1 to n, and again I'm approaching infinity. I'm going to take my 3I over n quantity cubed minus 6 3I over n when I substitute it into my function. Okay, so I'm substituting this into my function. That's what this means right here. Put it in for x. And then this is a constant, so we're just going to put it on the outside. Okay, when I do that and I simplify, I will have the limit as n approaches infinity. 3 over n is still on the outside. I still have my summation symbol. And I'm going to simplify this a bit, so this will be 27I over n cubed minus 18I over n. Now, hopefully here now you recognize that we could reduce that significantly. So what I'm going to do in this next point is I'm going to factor out my value. So actually, let's split it up because it's subtraction and we can split it up. I can have, now I know I'm going to have the limit here as n approaches infinity. I'm going to write it kind of small. And then I'm going to kind of mess with the inside. So here, if these two are separate, this would be 81 over n. And then I'm going to have I will go from 1 to n. And this is just I cubed. Oh, I'm so sorry. I forgot to put the cube to here. See, this is where I don't like not being able to speak to you guys all the time, because I know one of you would have caught that and said, hey, Doc. Okay, so here we have this. And double check. Okay, we're also going to bring out the n to the fourth, because this is n cubed times n. All right, so this is on the outside, and now I have I cubed here. So I'm going to do the next part. 3 times 18 will be 54 over, if I take out my n from the bottom 2, I'm going to have n squared on the bottom. And now I have my I equals 1 to infinity of I. Now, why did I do all of this? Well, I did all of this because, if you recall, before I showed you some ways that we can substitute in values that people already proved for you. Here, anytime I have the sum of 1 to n of I, it's equal to this. If I have the sum of 1 to n of I squared, it's equal to this. And if I have the sum of 1 to n of I cubed, it's equal to this. So I'm going to use these facts here to substitute it into my problem that I just did, so that I can simplify it even more. So hopefully I'm going to have enough room at the bottom of this page without cramming it too much. I now have 81 over n to the fourth Bum, 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 bum. And now my value, since I'm down here, since I'm going to, well, first let me put in this step. I'm rushing too fast, sorry, because I'm trying to save room, but I need to make sure you understand it. So I have n times n plus 1 over 2, and that's squared. Why? Because I substituted this in for this. Okay? And I'm going to do the same thing with minus 54 n squared, and then that's just times my I value, so that's n times n minus 1 all over 2. All right, now I'm definitely going to need more paper, so let me slide this up. Okay, slide it up to here. Now, I can see that if I square this and square this, this bottom is going to give me a 4. Okay, so then I'm going to move my n to the fourth over here, and I'm going to move my 4 over here. Why? Because that's going to help me simplify it. So now I have my limit as n approaches infinity, 81 over 4. Again, this is 2 squared. And then I have my n squared, n plus 1 squared over n to the fourth. Okay, now I do the same thing over here. And I have n times n minus 1 over n squared. Limit as n approaches infinity. So I can see now that I can divide by my highest degree. And we see that the highest degree for this one is going to be to the 4th power, and the highest degree for this one is going to be to the 2nd power. So I do need to clean that up so that we can see that a little bit better. So I'm going to use my binomial square here, n squared plus 2n plus 1, multiply it by n squared. Okay, I'm just doing this part here to simplify it. N to the 4th plus 2n cubed plus n squared. That is what's going to be on the top now. On the bottom is n to the 4th. Okay. Still have my 81 over 4 on the outside. That didn't go away. Over here, let's go ahead and do the same thing. Oh, this is minus. And I have n squared minus n over n squared. And hopefully all of you are looking at that going, hey, I know that when I take the limit as n approaches infinity of this rational expression, if the degrees are the same, it's just going to be what's in front. So it's just going to be 81 over 4 times 1. And this is going to be 54 over 2 times 1. Which, you know, we can reduce 54 over 2. Okay. At any rate, when I simplify this whole thing, I get negative 675. Negative 6.75 as my answer, and that will be evaluating it before, when we evaluated it using the Riemann sum, we got negative 3.9375 with only, when we do 6 triangles. So that's a bit off from what we actually did it with limits as it approaches infinity. So you can see how much better we can get. Now, here in the book, they do show you, here's what we're taking a look at. We know we're going to have a negative value because below the x-axis is negative. And over here, as I take a look closer, as my rectangles increase, maybe 40, 100, 500, 1,000, 5,000, and we can see we are definitely getting closer to the actual value that we got when we integrated it. Okay? Alrighty. Well, that was some work. Let's look at another one. Not as much work for 3, but we definitely still need to do another problem, maybe 2. Looking at example 3. And here I have x to the 4th dx. And remember, these together are a symbol. And part A says, set up an expression as the limit of sums. Okay, well, we can do that. So we have our delta x. Here, I'm looking at my upper and lower limit. So I'm going to have 5 minus 2 over how many triangles that I have. So that'll be 3 over n. And my f of x is x to the 4th. So let's take a look at my values. Since I'm starting at 2, my x sub 0 will be 2. My x sub 1 is going to be 2. Whatever that width is, depending on how many rectangles I have, will depend on what size this is. Okay, and then I'm going to continue that with 2 plus 3 over n, and I'm going to say 3 over n again. So I'm actually multiply this by 2. And then my x3 is going to be 2 plus 3 over n, and I'm going to do that 3 times, so I multiply it by 3. So my integral will be from 5 to 2, x to the 4th dx, limit as n approaches infinity from I equals 1 to n, whole bunch of rectangles, and I have my f of x sub I times my width. This is my generic, what I'm going to be taking a look at. So when I substitute in what I just developed up here, I will have my limit as n approaches infinity of 3 over n. That's my width, which is going to be a constant, so I can put it on the outside. And I'm going to run this from 1 to n, and I ended up having 2 plus 3i over n all to the 4th power. This is all to the 4th power. Okay? Remember, these are my x values. When I put it into my function, then I am going to raise it to my 4th power. All right, now, they say this one's pretty complicated, but you can find out from a computer algebra system that the value of this is going to be 618.6. So we didn't have to actually solve that one. They just wanted you to give this formula here. Okay? All right, now we're going to take a look at example 4. Example 4a. We take a look at looks like part of a circle. When I just glance at it here, we have 1 minus x squared. Okay, we know that's going to have to be, inside's going to have to be greater than 0, greater than or equal to 0. Okay, so we'll write that little piece of information down here because it's under a radical. And if I really take a close look at this in my brain, this is what I was thinking about. If I squared both sides, I can see that this is actually a circle. And my area that I'm looking at from 0 to 1 would just be in the first quadrant of the circle. So that's what I'm looking at, is my area under the curve of the first quadrant of the circle. So 1/4 of the circle. All right, so let's take a look at this. From 0 to 1, 1 minus x squared dx is actually going to be 1/4 of pi r squared. That's it. I don't have to do anything fancy here because I recognize that it's a circle, and I'm going to take my area of a circle and then take 1/4 of it because it's 1/4 of a circle, and that's all you need to do for that one. Okay. I think that should be good for now. We're going to take a look at the midpoint rule quickly. Now, we talked about taking values from the left and taking values from the right. Well, you can also choose a better value and just say we're going to choose the midpoint. Before we said if I had x sub I to asterisk, it could be anywhere in between the right and left value. That's correct. So if we decide we want that to be the midpoint of the interval, sometimes we may want to use that, as it may seem to give us a much better approximation. So we still have the width, b minus a over n, and we're going to take a look at the midpoints of where I'm starting to where I'm ending, take half of that, and use that value, that mean value for the x value. So here, if I have from 1 to 2 of 1 over x, my endpoints are going to be of 5 intervals, okay, 5 intervals, 5 rectangles. I'm going to have 1, 1.2, 1.4, 1.6, 1.8, and 2.0. So my midpoints between the two, midpoint between here would be 1.1, midpoint between here would be 1.3, midpoint between here would be 1.5, midpoint between here would be 1.7, and midpoint between here would be 1.9. So I would want to use those values to get an even closer estimate. In this case, I feel that it'll be a closer estimate, and I do the same thing that I did before with my right and my left, but this time I'm going to use my midpoints. Okay, some properties of definite integrals we need to go over. If I switch my upper and lower bound, I'm going to get a negative result. So if I switch my upper and lower bound, I'll get a negative result. If I have my upper and lower bounds the same as a definite integral, I will get 0. Some more properties of integrals. Here we can just put the c on the outside and take b minus a, where c is any constant. I can take them separately and add them together. I can differentiate my f of x and then take my constant times it, or I can find my differences as well separately and then subtract. Okay, continue on with section 4.2, starting with example 6. And we have the integral from 0 to 1 of 4 plus 3x squared, and then of course dx. Okay, so now we want to use the properties to evaluate. That's the directions. So let's take a minute and split this up, and we have 0 to 1 of 4 dx plus 0 to 1 of 3x squared dx. And we can take that a step even further and move the 3 out. 0 to 1 x squared dx. And 0 to 1 4 dx. Okay, so from property 1, we know that this will be 4 times 1 minus 0, and so that will give us 4 right here. And for the second part, we actually found in example 2 of section 4.1 that this right here was equal to 1/3. So we're using information that we got from previous problems to solve it. So now we have 4 plus 3 times 1/3, which is just 1, and that will equal 5. So that's it for example 6. Okay, and I'd say that's about it. So for 4.2, we can take a look at example 8 quickly. Actually, let's look at example 7 too. It's pretty simple. We can just glance at it here. We have from 0 to 10, f of x equals 17. We know that 0 to 8 is 12, and we want to find what 8 to 10 would be. So using property 5, we know that if we have 0 to 8 and then 8 to 10, we could add those together to get 0 to 10. Okay, so we're going to use the information that we have. We know that 0 to 10 is 17 and 0 to 8 is 12. And when we plug those in, we end up taking 17 minus 12, and the answer is 5. So that one is pretty simple. And then finally, section 8, we have a square root of x function. We're looking at it on the interval 1 to 4. We do know that by knowing the parent function, that the minimum will be at f of 1 would be 1, and the absolute max would be at 4, which is 2. And we'll take a look at that graph. Right here is, let me put it down so you can see it. That would be helpful, right? right here is the graph, and we can then estimate that we would have it be between my 1 value and my 2 value, both from 1 to 4. So we're going to say that my integral from 1 to 4 of the square root of x dx is going to be somewhere between the 3 greater than or equal to 3 and less than or equal to 6. And that is it for section 4.2. So there we go, and I will see you for section 4.3.